Hey, Dr. Clark coming back at you here. Another Green's theorem video using the circulation slash curl version of Green's theorem. So there's actually two versions of Green's theorem. In this one, what we're doing is we have some region, and what we want to know is that circulation around the outside. So imagine you've got some vector field F. You know, maybe the wind is blowing, wind is blowing, wind is blowing, wind is blowing. And you're in this little car, and as you go around the outside of that region, you know, maybe that wind blows you. Sometimes it's blowing against you, sometimes it's blowing with you. And so the integral of the vector field dotted with the tangent direction, ds, that gives you, you can call that, if it's a closed curve, you can call it circulation. We also call it, we would call it the work. So does the wind do some work on you? Or, you know, other context you might put on it. And what we're going to do is we're going to use Green's theorem to turn that into a double integral over the inside of something dA. So instead of doing that line integral around the outside, if we add up just all the things inside, then that will turn out to be equivalent to that work or that circulation that we were talking about before. It's going to be a closed circulation integral. And so if it turns out that this vector field is conservative, then we could use the fundamental theorem of line integrals and we would know that this is zero. So this is going to be more interesting for non-conservative vector fields, of course, but we can do it for them as well. But because we want to have a region R here, we want to do it for closed regions. Okay, so what's the idea? Remember, for the divergence theorem, we added up all these little divergences at every single point, but we noticed that those divergences canceled out, except on the boundary, then we got that net outward flux. Well, we're not talking about flux in this case, we're talking about circulation. So for every point, we want to have a way of adding up how much circulation is happening at that point. Then we go to the next point, and we add up how much circulation is happening there. And you'll notice that right at that point there, you get some cancellation. And here, it comes around, and there it's going up, and here it's going down. So you get cancellation. And here, cancels out, but then it goes there. But on the boundary, it doesn't cancel out on the outside. So if you take all these points and you add up sort of how much circulation is happening inside, they will always cancel out on any interior point, but on the exterior points, it won't cancel out. Now, of course, this is calculus, so we're doing this in an integral, so there's a limit as we sort of put in infinitely many more of these little boxes, and eventually it becomes infinitesimally small, and it's all happening at the limit. But that's the idea. We need to find a way to sort of quantify how much the vector field is causing you to turn around, okay? And what I want you to do is imagine yourself, you're standing in a river, and maybe the river's flowing really fast over here and really slow right there. What's going to happen if you're holding a board in the river? Well, you're going to get spun because this side of the river is pushing you really hard and that side of the river is not. So when a vector field changes as you move in the x direction, if these y vectors get stronger, that causes a rotation in you when you're trying to hold that board. So here, imagine this vector field kind of looks like this. Then when you're standing here, you're going to get rotated around. So you can see that the vector field, changes in the vector field can cause rotation. If the vector field sort of just is constant, you might get pushed along, but you're not going to get rotated. And so what we want to do is quantify all of these little rotations that are happening at these points. And so what I want you to do here is, if this is PQ, the vector field, then up arrows would be corresponding to Q, wouldn't they? And if Q is increasing as I move to the right. So if I take the x derivative of the y vector, if that is positive, then that's going to generate a counterclockwise curl or circulation. Similarly, if I'm standing in the river like this, and I'm holding my board, and the vector field sort of looks like this, then that's going to push me harder on this side than this side, and I'm again going to get spun around counterclockwise. So what I would want then is, well, this is the p part of the vector, right? This is the left-right. The p vector is actually decreasing when I move up. So the y derivative of p appears to be negative. That would be generating counterclockwise circulation. So what I want to do is really add the x derivative of q with the y derivative of p. And that has a name. This is called curl, or this, well, we're going to call it curl for now. Curl is going to get expanded later on, but we're going to call this curl in the same way that we called something that px plus qy, we called divergence earlier. We're going to call this curl. It's quantifying how much the vector field is causing you to curl around. So that's the main idea of Green's theorem. That gets turned into the actual theorem, which says that if you take qx and py, the negative of the py, and you add those up, that gives you how much circulation is happening. Okay, and we saw that right there. We had the qx and the negative of py. And so that's curl. So technically, curl is a property of F, and we're just pulling off the K component of curl. So when you have a vector field, the curl is actually a new vector field with itself 3 components, and what we're doing is we're just picking off that K component, because in this case, we're looking in 2 dimensions, and so the K vector, the ijk vector, is sort of, we're curling around that axis. So that's really what's going on. We're just going to think of this quantity as curl for the time being. So this is what this is saying. You could do the line integral to get that circulation around the outside, or you could use the Green's theorem to swap it out for an integral on the inside of this quantity qx minus py. All right? And this works, of course, if C is a simple, smooth, closed curve oriented counterclockwise, enclosing a connected, simply connected region in the plane. Okay? We want a simply connected region. That's important. We don't want any holes. And one last little thing. When a vector field has 0 curl, we call it irrotational, because if it's not curling around at all, it's not rotating, then you might get 0 over here, which would mean it's not circulating, so you won't get any circulation. So irrotational just means that curl is equal to 0. For our purposes, we're just pulling off the z component, or the k, the ijk, but k component of the curl. But actually, curl is its own vector field that you create from a vector field, which is kind of an interesting idea in and of itself. All right, let's do an example that will show you how this works. Here we go. We've got a channel of water. X is going from -1 to 1. Y is going from 0 to 10. And this water seems to be kind of flowing more quickly in the middle and then more slowly on the outside. And that would be similar, sort of all the way down the middle here. Okay, so it's a channel flow here problem. And what we want to know is there any circulation present? Okay, so what we're going to do is we're going to do double Green's theorem. We're going to do both sides of the integral and see that we get the right answer here. So first, if we did the line integral, we'd have to go around the outside of the vector field, dotted with the tangent direction, ds. Okay, well, around the outside, we've got a rectangle. There's actually 4 integrals to do here, but I think we're going to find that it's going to be pretty easy because the vector field F is going to be what? Well, over here, when x is equal to 1, you're going to get the vector field to be 0, 0. So this whole line here and here, F is equal to 0. So what happens when you take the 0 vector, dot it with t, you're going to get 0, and that's going to be 0. So it's going to be 0 plus 0 for the left and right side. And then what about the top and the bottom? For the top, well, the vectors are pointing this way, and the tangent vector would point that way. Those are orthogonal. So if f and t are orthogonal, when you dot product them, you get 0. So you're going to get 0 there and 0 on the bottom. So now we've got 0 plus 0 plus 0 plus 0. If we actually do the line integral version of the circulation, we're going to get 0. Okay, so it's the circulation is 0, but we should double check the other side of Green's theorem. So what does the other side of Green's theorem say? Well, it says that that circulation should also equal a double integral over the region of that curl quantity that we talked about, dA. And what was that curl quantity? Well, it was P, let's see, I got to make sure I get it. QX minus PY. QX minus PY. dA. Okay, so what was the vector field? P is 0. Well, that's easy. And Q is 1 minus x squared. Okay, so QX would be negative 2x. PY would be 0. We'll go dy dx, and I think we can integrate the x's from negative 1 to 1, and the y's from 0 to 10. That's the region. And then we just do this integral. 0 to 10, negative 2x, that's going to give us negative x squared, evaluated from negative 1 to 1. Oh, I got trouble here. dx, dy, I guess I wrote it. So that's going to give me 0 to pi, what, negative 1 minus negative 1. That's negative 1 plus 1, that's 0. And if I integrate from 0 to 10, 0, I'm going to get 0. Okay, so if we do the double integral, we get 0 as well. That's good because, you know, Green's theorem is true. We should get the same answer both ways. And there you can see that we do, in fact, get the same answer both ways. But really, we're thinking about it two different ways. Here, we're adding up, and really what's going on, think about your little guy in the water there. Here, he is getting turned, but he's getting turned clockwise. And the guy over here is getting turned counterclockwise because these vectors are bigger in the middle than on the left. So that guy gets turned counterclockwise, but over here they're bigger on the left than the right. So he's getting turned clockwise. And so we're actually getting this negative 1 plus 1 here is really telling us that we got some counterclockwise circulation here and clockwise circulation here, and they've canceled out. So you can see the calculus is actually communicating what's going on. So the vector field is not irrotational. It's not that it's irrotational. It's just that the rotation is balanced across the left and the right side. So that's kind of a cool problem as well. At the end of the day, it's really just turning these line integrals into a double integral you can do. And so once you kind of get the formula down, but I think it is nice to actually see the ideas that are in place here. It actually can make sense. It's not easy, but it can make sense if you think about what's going on. So hopefully you find that helpful, and we'll see you in the next video.